Algebra of Continuous Functions. Welcome back, everyone. Let's begin our discussion on the algebra of continuous functions. Up until now, in our previous sections, we have focused on the fundamental process of determining whether a single, individual function is continuous at a specific point. However, as we progress in mathematics, you will find that we rarely deal with simple functions in isolation. More often, we encounter complex functions that are constructed by combining several simpler functions together. This is where the algebra of continuous functions becomes incredibly useful. It provides us with a set of established rules that allow us to determine the continuity of these complex functions efficiently, saving us from having to apply the formal limit definition every single time we encounter a new expression. Essentially, the core idea is this. If we already know that two functions, f of x and g of x, are continuous at a specific point, x equals c, then any new function formed by adding, subtracting, multiplying, or dividing them will also be continuous at that same point. I must emphasize, however, that there is one very important exception regarding division, which we will explore in detail in the next slide. Fundamental operations. Now that we have established the concept of the algebra of continuous functions in the previous slide, let's dive into the fundamental operations. To begin, let's assume we have two real-valued functions, f and g, and we already know that both are continuous at a specific point, x equals c. Based on this, several important rules apply. First, let's look at the sum of functions. Simply put, the sum of two continuous functions is also continuous. This means that the function f plus g, which is defined as f of x plus g of x, is continuous at x equals c. The mathematical logic here is based on the properties of limits. The limit as x approaches c of the sum of f of x and g of x is equal to the limit of f of x plus the limit of g of x, which simply evaluates to f of c plus g of c. Next, we have the difference of functions. This follows a very similar logic to addition. The difference between two continuous functions is also continuous. Therefore, the function f minus g, defined as f of x minus g of x, is continuous at x equals c. Again, the logic is straightforward. The limit as x approaches c of f of x minus g of x equals the limit of f of x minus the limit of g of x, which results in f of c minus g of c. Moving on to the product of functions. If you multiply two continuous functions, the resulting product is also continuous. The function f times g, defined as f of x multiplied by g of x, is continuous at x equals c in terms of limits. The limit as x approaches c of the product of f of x and g of x is equal to the product of their individual limits, which gives us f of c times g of c. Finally, we have the quotient of functions. This is a critical point where we must be cautious. The quotient of two continuous functions is continuous, but only provided that the function in the denominator is not 0 at that point. Specifically, the function f divided by g, defined as f of x over g of x, is continuous at x equals c, provided that g of c is not equal to 0. The mathematical logic is that the limit as x approaches c of f of x divided by g of x equals the limit of f of x divided by the limit of g of x, which simplifies to f of c divided by g of c. These four operations allow us to build more complex functions while maintaining continuity. In the next slide, we will explore a few special cases that extend these basic rules. Special cases. Now that we have covered the four fundamental arithmetic operations, let's move on to two other important properties that often appear when working with continuous functions. First, let's look at the constant multiple property. Suppose you have a function, g of x, and you already know that it is continuous at a specific point, x equals c, if you multiply this entire function by a constant, which we will call lambda, representing any real number. The continuity of the function does not change. Essentially, the rule states that the function lambda times g is also continuous at x equals. See, this means that scaling a function vertically does not create any breaks or jumps. Next, we have the reciprocal function. This is very closely related to the quotient rule we discussed in the previous slide. If a function g of x is continuous at x equals c, then its reciprocal is also continuous, provided that the function's value at that point, g of c, is not equal to 0. To put it simply, the function 1 over g is continuous at x equals c, as long as we aren't dividing by 0. These rules, along with the basic operations, give us a powerful toolkit for analyzing complex functions. To help you visualize how these concepts apply outside of a textbook, I will now share a real-world analogy in the next slide. Real-world analogy. Now, to help you visualize the formal rules we have just discussed, let's look at a real-world analogy. Imagine you are in a laboratory with two separate sensors. Sensor A, which measures temperature, and sensor B, which measures pressure. In this scenario, if both sensors are stable, meaning their readings change smoothly over time without any sudden, erratic jumps, they are essentially behaving like the continuous functions we have been studying. Now, consider what happens if you combine these readings. If you create a new metric by adding the temperature and pressure together, or multiplying them to calculate a specific gas constant, the resulting value will also remain stable. This directly mirrors the sum and product rules we saw in the previous slides. The combination of two continuous functions remains continuous. However, there is a critical exception when it comes to division. If you divide the temperature by the pressure, the result will generally remain stable. But if the pressure ever drops to 0, the calculation becomes undefined and breaks down completely. This is a perfect illustration of a point of discontinuity, reminding us why we must always ensure the denominator is not 0 when applying the quotient rule. Keeping this analogy in mind will make the practical example we are about to see in the next slide much easier to understand. Step-by-step example. Now that we have established the fundamental rules and explored a real-world analogy, let us apply these concepts to a practical problem. Please look at the example on the screen. Our objective is to determine if the function h of x, which is defined as x squared times the sine of x, is continuous for all real numbers x. Instead of applying the rigorous limit definition, we will use the algebraic rules we just discussed. Step 1 is to identify the component functions. If we examine h of x, we can see that it is constructed as a product of two simpler functions. Let us define the first function, f of x, as x squared, and the second function, g of x, as the sine of x. Step 2 is to analyze the continuity of each of these individual components. First, consider f of x equals x squared. This is a polynomial function, and as we have learned in our previous sections, all polynomial functions are continuous for all real numbers. Next, we look at g of x equals the sine of x. This is a basic trigonometric function, which is also continuous for all real numbers. Step 3 is to apply the algebra of continuous functions. Since h of x is the product of f of x and g of x, and we have already confirmed that both components are continuous everywhere, we can simply apply the product rule. As we saw in the fundamental operations slide, the product of two continuous functions is also continuous. Consequently, we can reach the conclusion that the function h of x equals x squared times the sine of x is continuous for all x belonging to the set of real numbers. While this process is straightforward, it is easy to overlook certain details. So in the next slide, we will discuss some common mistakes to avoid when applying these rules. Common mistakes. Now that we have seen how to apply these rules through a practical example, it is crucial to discuss some common pitfalls that students often encounter. Let's look at the common mistakes slide. First, let's talk about ignoring the denominator. The most frequent error I see is the assumption that the quotient of two continuous functions is always continuous. As we discussed in the fundamental operations and the sensor analogy, this is not the case. You must always verify whether g of c equals 0. If the denominator evaluates to 0 at that specific point, the function is discontinuous there, regardless of the continuity of the numerator. Secondly, there is a frequent conceptual confusion between continuity and differentiability. Many students assume that if a function is continuous, it must be smooth. While the algebra of continuity ensures that the function is unbroken and has no gaps, it does not guarantee that the function is differentiable. A classic example is the absolute value of x. While the absolute value of x is continuous everywhere, it is not differentiable at x equals 0 because of the sharp corner at the origin. Finally, be careful about applying these rules to functions that are already discontinuous. It is important to remember that these algebraic properties only hold if the starting functions, f and g, are already continuous at the point in question. You cannot use the sum rule to prove that a combined function is continuous if one of the individual components is already discontinuous. Keep these warnings in mind as we move toward our final summary of the key takeaways. Key takeaways. To wrap up our lesson on the algebra of continuous functions, let's go through the key takeaways to ensure you have a solid grasp of these rules before we move on to more complex problems. First, let's recap the basic operations we discussed earlier. If the functions f and g are both continuous at a point C, then their sum, difference, and product, represented as f plus g, f minus g, and f times g, are always guaranteed to be continuous at that same point C. These are the most straightforward rules, and as we saw in our step-by-step example, they allow us to analyze complex functions by breaking them down into simpler parts. Next, we have the quotient. The function f divided by g is continuous at point C, but only under one critical condition. The function in the denominator, g of c, must not equal 0. As we highlighted in the common mistakes section, always remember to check the denominator first, because a 0 value here creates a point of discontinuity. Moving on to constants, remember that multiplying any continuous function by a constant lambda, where lambda is any real number, preserves its continuity. This means the overall behavior of the function remains stable and unbroken. Finally, let's look at reciprocals. The function 1 over g is continuous wherever g is continuous, provided that g of x does not equal 0. This follows the same logic as the quotient rule we just discussed. We must ensure we aren't dividing by 0. By keeping these fundamental rules in mind, you can confidently determine the continuity of almost any combined function without having to rely solely on the formal limit definition every time.